if the velocity versus time graph has constant slope, then the most general form of the velocity function, well, the velocity function, if we have constant slope, then v is a linear function of t. That is, the slope being constant, your graph is a straight line, and that's what it means for v to be the linear function of t. In the general form of a linear function can be expressed at plus b, a linear function of t. A would be interpreted as the slope, be interpreted as the vertical axis intercept. So, a and b are constant. Again, a is the slope, b is the vertical intercept, or the v-intercept. In this case, v being the quantity that's on the vertical axis. Okay, so now another situation. If v of 0 equals 0, then what's the most general form of the equation or the function that results? Well, in that case, v of 0, well, first of all, v of t is equal to at plus b for some a and b. If v of 0 equals 0, then v of 0 being equal to a times 0 plus b is just equal to b. And if that's 0, then we have b equals v of 0. And if v of 0 is 0, then, and I don't think I really answered this question in class, then v of t equals at. If v of 0 equals 0, v of t then equals at, since b equals v of 0. Okay, so there's our most general form if the initial velocity is at the t equals 0 instant, and if that initial velocity is 0. Now, in general, whatever v of 0 is, our v of t function is at plus v of 0, and we will generally indicate that by at plus v sub 0. V sub 0 being v of 0, unless we define it otherwise. Well, now, another question. If v of 0 is 70 centimeters, then what's the most general form? Well, if we substitute 0 for b, substitute 0 for t, then v of t is going to equal b, so that if v of 0 is 70 centimeters per second, well, we can come down to this form. At plus v of 0 will be at plus 70 centimeters per second. Now, ignore this stuff down here. It kind of grew from over here, and we'll get to that in a minute. Okay, well, if v of 10 seconds is 200 meters per second, then what do we have? Again, assuming that v versus t has constant slope. Well, again, our general form is v of t equals at plus b, so that v of 10 seconds is a times 10 seconds plus, and I have v of 0 down there. That's probably not correct. Okay, I got a little confused. I was going back to the original form. This is going to apply if we have the form v of t equals at plus v of 0. So again, in this case, then, if this is the function, v of 10 seconds is a times 10 seconds plus v of 0. And then if v of 10 seconds is 200 meters per second, we have 200 meters per second equals a times 10 seconds plus v of 0, which tells us that v of 0 is 200 meters per second minus a times 10 seconds. Now, let's think about what that means. A times 10 seconds is the amount by which the velocity changes in 10 seconds. A being the acceleration, which is the rate of change of velocity with respect to clock time. We multiply that by the change in clock time, and we get the change in velocity. So between 0 and 10 seconds, the change in clock time is 10 seconds, and the change in velocity will be a times 10 seconds. So we get v of 0 is 200 meters per second minus a times 10 seconds. That is, the t equals 10 velocity minus the velocity it picked up between 0 and 10 seconds. So then we get v of t is at plus v of 0, which is 200 meters per second minus a times 10 seconds. That could in turn be manipulated. We have an A term here and an A term here. We can factor out the A, and we get between this term and this term, A times t minus 10 seconds plus 200 meters per second. Now this is the form of a graph that's shifted 10 seconds to the right from an AT plus 200 meter per second graph, and that can be interpreted, but let's not go into that right now. But keep in mind that when you replace t by t minus 10 seconds, you do have a horizontal shift in your function, and that can be a useful thing for imagining what's going on. Okay, let's move to the usual way, though, that you're going to use this general AT plus B form. Let's say that you know, okay, let's back up a second. In each of these cases, you were given one piece of information. In this case, you were given the velocity at time t equals 0, and that allowed you to express the velocity function in terms of that t equals 0 velocity and just the acceleration, and of course the time variable. So we don't have a b term in here anymore. We identify the b term as v of 0, the velocity at the t equals 0 instant. And of course that applies here too. Now we no longer have a b in here. We have a definite quantity, 70 centimeters per second. In this case, again, we eliminate the b in terms of our v of 0 and then in terms of our 200 meters per second. So we've eliminated one of the parameters, a and b, of this general velocity function. Now if we know two quantities, v of 0, say, and v of 10 seconds, we're going to be able to eliminate both a and b and express the result as simply a numerical equation. Okay, so now in general, if we have two values, if we have values of v at 2 times, we get two equations. If v of 0 equals 70 centimeters per second, we have a times 0 plus b equals 70 centimeters per second using this form. And if at 10 seconds we have a 200 centimeter per second velocity, and I'm switching back and forth between meters per second and centimeters per second, so let me fix that real quickly. There was really nothing wrong with having this in meters per second, except that it's not going to mesh with what we have down here, and the intent was that these should mesh. So I've changed the meters to centimeters. Everything is the same except that unit. Okay, again, the first equation we get, substituting t equals 0 and setting our AT plus b equal to 70 centimeters per second, we get this equation. Now, it's clear that since this is a times 0, we just get b equals 70 centimeters per second. I'm not going to actually use that. I want to illustrate a more general way of solving these equations, which I'm sure you're familiar with, but let's go on. So if we plug in 10 seconds, we get a times 10 seconds plus b, and if that's equal to 200 centimeters per second, then we have a second equation. So now we have two equations in two variables, a and b. We can solve for the two parameters a and b. Now I could have solved the first equation for 70 centimeters per b equals 70 centimeters per second and plugged that in here and very quickly been able to solve for a. I'm going to go the other way around, not because that's what we would really want to do here, but again because it's more illustrative. Solving this equation for b, I get b equals 200 centimeters per second minus a times 10 seconds, and that's very obvious. And then I take that and plug it in for b here, and that gives me this equation, a times 0 plus b, which is 200 centimeters per second minus a times 10 seconds. Encircling this thing, I obscured some of that, but this is just your 200 centimeters per second minus a times 10 seconds that we have more clearly here. And I've just substituted that for b, and then on the right-hand side, I get my 70 centimeters per second. And that second got blurred in transporting the board, but let's make sure we can see that. Okay, and solving that is quite simple. A times 0 is 0. We can add the 200, well, subtract the 200 centimeters per second from both sides. On this side, we'll get negative 130 centimeters per second. On this side, we have negative a times 10 seconds. Dividing both sides by 10 seconds, we get a equals 13 meters per second squared, but it should be centimeters per second squared. Then, got one more correction to make. Then plugging this 13 centimeters per second squared back in here for A, we finally get B equals 200 centimeters per second minus 13 centimeters per second squared times 10 seconds, which is going to give us, this term is going to give us negative 130 centimeters per second, so that B will end up being 70 centimeters per second, as we already knew it would. Then we have our V of t function, 13 centimeters per second squared times t plus 70 centimeters per second. Some of this is a little hard to read, but it's very straightforward, and you should be able to do it. But let me just kind of write a couple of final results on the board to make sure. I've had to write it a little smaller than I'd prefer, but this equation here just comes from plugging our 13 centimeter per second squared value for A into this expression. We have 200 centimeters per second squared minus 13 centimeters per second squared multiplied by 10 seconds, and you can verify that it comes out 70 centimeters per second. Then our final function here, which I could write a little more clearly up here, although I don't think it's going to win any awards, is AT plus B. A is 13 centimeters per second squared, that's multiplied by t, plus B, which we just determined to be 70 centimeters per second. Again, the main idea here is that we have, if we know that V versus t is linear, we know that the V function, the velocity function, has to be of the form AT plus B. And if we know the velocity at two different times, for example, we can write two simultaneous equations to evaluate evaluate the parameters A and B and solve those two simultaneous equations by whatever method.